All right, so where we're going to start talking about in kinematics is to talk about average kinematics. And so our average kinematical quantities are basically quantities that only care about what's going on at two particular points in time. So your initial point in time and your final point in time. All the details in what you do between those 2 points in time actually gets completely washed out. So for our average kinematical quantities, we're going to start by saying, all right, so we know that we keep track of where an object is located at any point in time by talking about its position. And so for us, we're going to use r vector as the position vector. In this case, if we've got motion in the xy plane, so we're not worried about things in z into or out of the plane, but we would say, hey, your position is just the vector that runs from the origin to your object's location. It's got components of x and y. So I can break up the position vector and think about its three components. So x, where it's located in the x direction, what its x location is, y, what its y location is, and then z, what its z location is. And again, here we've sort of set it up so that z is going to be 0 in terms of this picture. So this is what the position vector is telling me. So in terms of our table, and if I want to break this up, the position vector is very easy to break up. So with displacement, we see that displacement is defined to be the change in position. So this just means the final position minus the initial position, and so this is really a vector subtraction problem. And so what we see is we're going to work this the way we would work any vector subtraction problem. We're going to break up our final vector into its x and y components. We're going to break up the initial vector into its x and y components. Then we'll just do final minus initial to get the x component of the displacement, final minus initial to get the y component of the displacement. So our picture, and our vector diagram, we've now got two position vectors. Here's the one for the initial point in time, here's the one for the final point in time. And so we've calculated out the components using our table. Again, if we wanted to include what was going on in the z direction, we'd have a third component to deal with. But it works just like the other two. And so when we draw this out, we said the displacement vector is the vector that runs from the tip of the initial to the tip of the final. So literally just where the object was to where the object is. Now the average velocity we're basically going to build using the displacement. So notice the displacement just cares about where you were and where you are. The average velocity cares about where you were and where you are and how long it took you to get there. So the average velocity is taking the displacement and now also including this factor of time. The top of this, in terms of our definition for the average velocity, the top of this, again, that's just a vector subtraction, and this is really just a scalar, right? So we know time is a scalar, so if I subtract time between 2 points, that's just a scalar. So again, I go do my vector subtraction problem first, so set up the components for the final vector, final position vector, initial position vector, do my vector subtraction. And then all I need to do now is take each of these components, so here's the component of the displacement, and now divide by my change in time. So I get that the x component for the average velocity is just going to be delta x over delta t. The y component for the average velocity, delta y over delta t. Z component, delta z over delta t. Now, the other thing to notice here is, again, that you can think of this as I'm taking a vector and multiplying it by a scalar. That scalar happens to be 1 over delta t. Since delta t is always positive, 1 over delta t is always positive. So what this means is I'm multiplying my displacement vector by a positive scalar to get the average velocity. That tells me that the average velocity and the displacement have to point in the same direction. So the average velocity always, always, always points in the same direction as the change in position, right? That's just another way of saying the displacement. So here is our picture where we say the average velocity points in the same direction as the change in position, as the displacement vector. Now there's an average quantity that I can talk about that's not a vector, and that's the average speed. And so we need to calculate this one a little bit different, right? So because it's not a vector, we've sort of got a different process. I don't need to break this up into x and y components. The difference here is that the average speed actually does care about the path that the object takes from the final point to the initial point. So that path is a very different path than, say, if the object had just walked straight there. So the average speed will only be equal to the average velocity in the special case where the object walks along a straight path from its initial point to its final point. If the object basically turns off of that line at all, then those two things will not be the same, because the object will be now needing to cover an additional distance that's not going to factor into the displacement. So our average speed, the way we calculate it, is I need to know the total distance that the object traveled, divide that by my chunk in time. So clearly, if it took the same time to go all the way around here and travel this much longer path than it did to just go straight from my initial point to my final point, that's going to require a much larger average speed, even though the average velocity for both those situations would be exactly the same. So average speed, it's a lot like average velocity. They can give us the same value in certain circumstances, but they're not the same thing. The last quantity that we want to add is the average acceleration. And again, here, just by definition, it's the change in velocity over change in time. So when we introduced the idea of acceleration, we said that the acceleration is telling us about how the velocity changes with respect to time. And so the average acceleration just says, tell me what your velocity was at some initial point, tell me what your velocity is at some final point, work the vector subtraction problem. So again, I'm going to set this up as x and y components of the final velocity, x and y components of the initial velocity, and then I just need to do the subtraction. So I get to work a vector subtraction problem to tell me about how the velocity is changing, and then divide by time. So again, if I think about the components of the average acceleration, it's the change, so the x component of the average acceleration is just the x component of the change in velocity divided by time. Y component of the average acceleration is just the y component of the change in velocity divided by time. And again, if you want to deal with z, it's the same thing. The z component of the average acceleration is just the z component of the change in velocity divided by time. Again, in this case, what this means is, because again, I'm taking the change in velocity vector and multiplying it by 1 over delta t, a scalar that's always positive. So again, this tells me that the average acceleration points in the same direction as the change in velocity. So one of the biggest points of confusion for students is that they'll want to make the average acceleration vector point in the same direction as some velocity, but they'll pick the wrong velocity vector. So what we want is we want the change in velocity vector. That's the one that's always going to point in the same direction as the average acceleration. So these are the 4 quantities that we're basically going to care about in terms of motion between 2 points in time. So we're going to care about the displacement, the change in position, the average velocity, the average speed, and the average acceleration.